Section 2.3.4, modeling overdamped motion. In the case of systems where we have zeta is greater than 1, that's where we have overdamped motion. And again, we're trying to find solutions for lambda, and we have distinct real roots. That means that lambda 1 is equal to negative zeta omega n minus omega n square root of zeta squared minus 1. And we have lambda 2 is equal to negative zeta omega n plus omega n, the square root of zeta squared minus 1. Which means the solution for the equation of motion, using the same assumed solution that we had before, becomes x of t is equal to e negative zeta omega n t multiplied by lowercase a1 e to the negative omega n t square root of zeta squared minus 1 plus a2 e positive, I'm just going to put this there to be explicitly clear, it's definitely not needed, omega n t, the square root of zeta squared minus 1, all of that in brackets. And again, that is a solution that allows us to solve for any moment in time, x of t, the time that we want. So this equation represents a non-oscillating response. Oscillating response. And again, A1 and A2 have to be solved for the boundary conditions. We can get those by setting So the square root's in the exponent. Maybe I can draw it like that so you know. We need to solve for A1 and A2. We get those by solving x0, putting t equals to 0, solving for your displacement, taking the derivative of x dot, putting it equal to 0, solving for your velocity, right? We can do that. We know how to do that. But how about I just write down the answers if we were to walk through all of that? That seem fair? Save us some time, because an overdamped system is not the purpose of this class. I get A1 is equal to negative V naught plus negative zeta plus the square root of zeta squared minus 1 omega n x naught over 2 omega n square root of zeta squared minus 1. And that gives us A1 and A2. We can find using the same approach, setting t equals to 0 for x and getting velocity, getting x dot, setting t equals to 0. And we can get V naught plus zeta plus square root of zeta squared minus 1 omega n x naught over 2 omega n square root of zeta squared minus 1. And that gives us a full solution for an overdamped system. And we can again, create systems that just sort of arbitrarily figure 2.25 in the notes, draw some of these out. But if we were to just go time and amplitude, right, we might have something that comes up if we have an initial velocity with the system, but it's going to come right back down and not cross zero. Or we might have something that has no initial velocity, kind of comes out flat, comes down, crosses zero. I guess you could even have something with negative initial velocity. Let's use another color. Ooh. But nothing ever crosses zero because nothing ever oscillates. And that's an overdamped system.